In the previous videos, we focused on the wave nature of light and then the particle nature of light separately. Now that we have a foundation for the way waves behave and the way particles behave, we're going to look at both of these when we discuss matter here in one video. So now we're going to look at the dual nature of matter, meaning it will act as both a wave and as a particle. And we're going to focus a lot here on electrons. So, mhm. So electrons act as a particle, and if you drew at the beginning of this lesson, an electron was some sort of sphere with a negative charge, small, yes, but does have mass, then you are not wrong. An electron, if we just take a measurement of ejected electrons, we'll be able to see them appear as individual particles on like a photo paper. Um, and as more electrons are ejected, we'll see an increase. And if you look at this, there's no real pattern to it, right? It's a random smattering of electrons on this photo paper, which would be consistent with a particle being ejected from a source and striking this paper in one spot. And so this is the behavior that we're used to for matter in general, similar to how we expected light to behave as a wave. So Louis de Broglie, in the early 1900s, proposed that particles could actually behave like waves. Similar to how waves could be both a particle and a wave, so could matter. Um, and he predicted that the wavelength of the particle would be inversely proportional to its momentum, so how fast it was going. Um, and this is going to be pretty insignificant for large objects like ourselves because we are big and have lots of mass. But he said that for objects that are small, very, very, very small, and have a very small mass, that wave character that it has would become a significant part of its behavior. So he's saying that we have wave behavior, and so does my computer, and so does the couch I'm sitting on. But because our mass of myself, the couch, and the computer are so large that we can't actually observe that wave behavior, and it doesn't play a significant role in how we move through space. And so, this relationship between mass and the speed of a particle, um, the velocity of the particle and its wavelength, is given here. This is de Broglie's equation that relates these ideas. And so, we have our wavelength is equal to Planck's constant divided by the mass of the particle times the velocity of its particle. And I know that velocity and frequency look very similar in the way they're written as variables. In this case, when you see it by the m in these equations, we're looking at the velocity of the particle with a specific mass. And so we can imagine it that if this mass is very, 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 very large, then that would make this entire value here, which is equal to the wavelength, very, very, very small. And that is why we don't see significant wave character for large objects. But if this mass is itsy bitsy, really, really tiny, then we'll see a wavelength that is larger, that is more significant. And that's why we can see wave-like behavior for your an electron, which is super tiny and has oftentimes we call it a negligible mass when we compare it to things like a proton, which has an extremely small mass. So here is an experiment looking at waves. So remember how we showed earlier that we wouldn't really have a pattern if we had if we kept shooting electrons at photographic paper, right? Well, so if these electrons only acted as a particle, then if we did a double slit experiment where we were using photographic paper here to track where electrons hit, and we were shooting electrons through a barrier that had two slits, we would expect to see two places where particles that were able to go through the barrier would hit our paper, our photographic paper. But we don't see that. We don't see that expected behavior for a particle. Instead, what we see is lots of places where the electron hits the photographic paper, and it's interspersed with areas where it doesn't hit it at all. Now, this pattern, if you remember from when we talked about light, is a diffraction pattern. So over time with a double slit experiment, we get to a picture right here where we have places of high intensity electron where the electrons have hit a lot, and areas where they haven't, where less electrons have hit. And so this develops into a diffraction pattern that matches the way light behaves. And so we can observe wave behavior from a stream of electrons that we are used to thinking of as particles. So coming back to how we draw electrons in light, you're not wrong to draw an electron as a particle and light as a wave at all. But you also wouldn't be wrong to draw an electron as a wave and light as a particle. And so here's one interpretation of this for an electron is drawing an electron as a wave that is a particle when it hits something. Or I always draw mine as a wave with a little head right here. It's like it's a packet of light. So it's a particle and it's a wave, traveling in a wave.